Welcome! Today we're going to solve a fascinating and surprisingly common problem you might encounter in math puzzles and competitions. Our goal is to find the value of x in the equation x to the power of x to the power of x, which equals 256. This might look intimidating at first glance, but by the end of this video, you'll be able to solve it and understand the logic behind it. We'll explore two main approaches, one based on pattern recognition, and a more rigorous algebraic method using exponents and logarithms. Let's get started. Let's start with an intuitive approach, one you might call educated guessing or pattern recognition. The first step is to focus on the right-hand side of our equation, the number 256. The equation is x to the power of x to the power of x equals 256. We need to figure out what kind of number 256 is. Is it a power of something? Let's check some common powers. For example, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, and so on. We can keep going until we find 256. 2 to the 7th is 128, and 2 to the 8th is 256. So, we found that 256 can be written as 2 to the 8th power. Let's substitute that back into our equation. Now we have x to the power of x to the power of x equals 2 to the 8th. This form still doesn't quite look the same. Our equation has a repeated base of x, and here we have 2 and 8. Let's try to rewrite the right side, 2 to the 8th, in a different way that might look more like the left side. What if we try to write it with a repeated base? Let's take 8 and see if we can write that as a power of 2. We know that 8 is equal to 2 to the 3rd, so we can replace the exponent 8 with 2 to the 3rd. Our expression becomes 2 to the power of 2 to the power of 3. Now let's compare this to our original equation. On the left, we have x to the power of x to the power of x. On the right, we have 2 to the power of 2 to the power of 3. They don't match up perfectly yet. The 3 at the top is the problem. What else could we do with 2 to the 8th? We know that 2 to the 8th can also be written as 2 to the 2nd power raised to the 4th power. That's using the rule a circumflex b circumflex c equals a powered bc. 2 to the 8th is also equal to 2 to the 2nd to the 4th. And 2 to the 2nd is 4, so this is just 4 to the 4th. Now let's see if 4 to the 4th is a repeated power. No, the base is 4, and the exponent is 4. This is a very nice symmetric form. So now our equation looks like this. X to the power of x to the power of x equals 4 to the power of 4. Look closely at the pattern here. On the left side, we have x repeated 3 times. On the right, we have 4 repeated twice. It still doesn't look like an exact match, but it's much closer than before. A base of x to the power of x equals a base of 4 to the power of 4. This strongly suggests that x equals 4. Let's confirm this by substituting x equals 4 into our original equation. We get 4 to the power of 4 to the power of 4. Now, the key is to solve this by working from the top down. 4 to the power of 4 is 256. So we have 4 to the power of 256. This is a massive number, far too large to equal 256. So x equal sign 4 is incorrect. This tells us that the simple pattern matching we did isn't enough, because we have a tower of exponents. Let's go back to our starting point and try a different approach. Let's re-examine our starting point. We have x to the power of x to the power of x equals 256. This time, let's treat the exponent as a single entity. Let's introduce a variable to make this clearer. Let's say that y equals x to the power of x. By making this substitution, our equation becomes much simpler. It's now x to the power of y equals 256. Remember, our goal is to find x. To get rid of the y in the exponent, we can raise both sides of the equation to the power of 1 over y. So we have x equals 256 to the power of 1 over y. Now, we have two expressions for x. We know that x equals 256 to the power of 1 over y, and we defined x as the base of our original expression, x. We can set these two expressions equal to each other. This gives us a new equation. X equals 256 to the power of 1 over y. This looks a little circular. Let's try to manipulate this and bring y back into the picture, using its definition. We have x equals 256 to the power of 1, and we know y equals x to the x. Let's substitute x to the x for y in the exponent. This doesn't seem to simplify things directly. Let's try a different strategy based on the equation x to the power of y equals 256. We have x to the y equals 256. Let's go back to our pattern recognition idea. Can we find a simple number x that makes this work? Let's re-express 256 as 4 to the fourth. So x to the power of y equals 4 to the power of 4. From this, it's very tempting to say that x equals 4 and y equals 4. Let's test if this is a valid solution. Remember, we defined y to be x to the power of x. If x is 4, then y must be 4 to the power of 4. So, our candidate for x is 4. This means y must be 4 to the fourth, which we already calculated as 256. But our equation x to the y equals 4 to the fourth suggested y equals 4. We have a contradiction. This means x equals sign 4 is not the correct answer, which we confirmed with our earlier check. This shows why just matching the pattern isn't enough when the exponents are also variables. So, we've seen that educated guessing and simple pattern matching can be misleading. Now, let's use a more robust algebraic method. Our key insight will be to make the form on both sides of the equation match. We have the equation x to the power of x to the power of x equals 256. The left side is of the form a to the power of a. We want the right side to also be in this form. Let's rewrite 256 as 2 to the 8th again. We have x to the x equals 2 to the 8th. We need the forms to be identical. Let's raise both sides to a power that will simplify the left side. Let's raise both sides to the power of x. This might seem counterintuitive, but watch what happens. On the left side, we use the exponent rule. A point B better day, c equals a point bc. So we multiply the exponents. This gives us x to the power of x times x to the power of x. This might not look simpler, but it's okay. On the right side, we also multiply the exponents to get 2 to the power of 8x. Now, let's use another exponent rule. When we have the same base multiplied, we add the exponents. The exponent on the first x is 1. So, on the left we get x to the power of 1 plus x to the power of x. This doesn't look promising either. Let's try something else. There's a much more direct way. Let's return to x to the x to the x equals 256. Our goal is to make the entire left side look like a base raised to that exact same base. Let's try raising both sides to the power of x to the power of x. So we have x to the power of x to the x, all raised to the power of x to the x. On the right, we have 256 to the power of x to the x. Let's simplify the left side. Let's call the entire exponent x to the x by a letter, say a. So we have x to the a to the a. Using the exponent rule, a point b2z equals a point bc, this becomes x to the power of a times a, which is x to the power of a squared. This is x to the power of x to the x squared. This looks very close to our target form. Let's rewrite it slightly. We can write this as x to the power of x squared to the x. This is not quite right. A better way to write it is x to the power of x to the x to the power of x to the x. This is getting messy. Okay, let's reset and take a clean algebraic approach that is much more effective. Our equation is x to the x equals 256. The key is to apply a logarithm. Let's use the natural logarithm, ln, on both sides of the equation. This gives us the natural log of x to the x equals the natural log of 256. Now, we use the logarithm property that the log of a number raised to a power is the power times the log of the number. That is, ln a to b equals b times ln a. In our case, the base is x, and the exponent is x to the x. So, we can bring x to the x down in front of the logarithm. Our equation becomes x to the x times ln x equals ln 256. We've made progress, but we still have an x on both sides of a multiplication. Let's use another property of logarithms. We know that e raised to the power of ln and y is simply y. This means we can write x as e to the power of ln x. Let's substitute e to the ln x for x in our equation. We get e to the ln x raised to the power of e to the ln x times ln x equals ln 256. This might look more complicated, but it's not. Let's simplify the first part. Using the exponent rule, a point b, z equals a point bc. The exponents multiply. So we have e to the power of ln x times e to the ln x. This is not correct. The exponent in the first part is x to the x. So we have e to the ln x raised to the power of x to the x. This becomes e to the power of x to the x times ln x. Wait, this is the same as the step we had before, just written differently. We're on the right track. We are at the equation x to the x times ln x equals ln 256. Now let's use the substitution we were trying to make earlier. Let z equals ln x. If z equals ln x, then x must be e to the power of z. Let's substitute these into our equation. Again, using the exponent rule, a point b, c equals a point bc, we multiply the exponents. We get e to the power of z times e to the z multiplied by z equals ln 256. This looks like a difficult equation to solve. There's a special function, the Lambert W function, designed to solve equations of the form y-y equals z. This is exactly what we have. Let's introduce the Lambert W function. It's also called the product logarithm. The Lambert W function, written w of z, is defined as the function that gives you the value y, such that z equals y times e to the power of y. It's the inverse function to f of y equals y times e to the y. Let's rearrange our last algebraic equation to match this form. We had e to the power of z times e to the z multiplied by z equals ln 256. Let's use the exponent rule, a par bc equals a circumflex b circumflex c. So we can rewrite the left side as e to the power of z times e to the z times z equals ln 256. This doesn't seem to get us closer to the y form. Let's go back one step further to the equation x to the x times ln x equals ln 256. We had x to the x times ln x equals ln 256. Now, let's substitute x equals e pash ln x directly. This was the key. We get e to the ln x raised to the power of e to the ln x multiplied by ln x equals ln 256. Let's simplify the first part using the exponent rule. A point bz equals a point bz. The exponents multiply, so we have e to the power of e to the ln x times ln x multiplied by ln x equals ln 256. Let's rearrange this. Let's group the terms to look like y times e to the y. We can write it as ln x times e to the power of ln x times e to the ln x times equals ln 256. This is getting close. Let's make a new substitution. Let u equals ln x times e to the ln x. Our equation simplifies to u times e to the power of u equals ln 256. This is exactly the form for the Lambert W function. We can now solve for u. Applying the definition of the Lambert W function, u must be equal to w of ln 256. So we've found u, now we need to back substitute to find x. Remember, u was defined as ln x times e to the ln x. So, we have ln x times e to the power of ln x equals w of ln 256. Notice the left side is in the form y times e to the y, where y is ln x. We can apply the w function to this side as well. W of back n dash times e to the ln dash x equals ln x, and this equals w of ln 256. We're almost there. We have solved for ln x. To find x, we just need to exponentiate both sides with base e. So x equals e to the power of w of ln 256. This is the exact solution. We have our exact solution, x equals e to the w of ln 256, but this value isn't obvious. We need to evaluate the w function. For integer inputs, the Lambert W function can sometimes be found by rearranging powers of e. For example, w of e is 1 because e equals 1 times e to the first, and w of 2e squared is 2. Our input is ln 256, Since 256 is 2 to the 8th, ln 256 is 8 times ln 2. So we need to find w of 8 ln 2. This is not an integer or a simple multiple of e, so we'll need to use a calculator or approximation. However, there's another way to solve this specific problem that bypasses the Lambert W function, by being very clever with exponents. Let's return to the equation x to the x times ln x equals ln 256. The left side, x to the x, tnx, is not in the correct form for wy equals y dash e minus y. But what if we could make it look like a number raised to itself? Remember the property a to the b equals e to the power of b times ln a. Let's apply this to x to the x. It becomes e to the power of x times ln x. Now substitute this back into our equation. We get e to the power of x times ln x, all multiplied by ln x, equals ln 256. Let's bring the ln x term inside the exponent using the rule b times ln a equals ln a to the b. This gives us e to the power of ln x to the x times ln x equals ln 256. This rearrangement isn't simplifying it. There is a simpler path. Let's restart the algebraic method. Sometimes a direct substitution is best. We have x to the power of x to the power of x equals 256. The left side is of the form a to the a, where a is the expression x to the x. We can write this as x to the x raised to the power of x to the x equals 256. Now, let's substitute a variable, say y, for the repeating expression x to the x. So, we let y equal x to the x. Our equation becomes much cleaner. Y to the power of y equals 256. This is a simple power equation we can solve directly. We're looking for a number that, when raised to itself, equals 256. Let's test integer values. 1 to the first is 1, 2 to the second is 4, 3 to the third is 27, 4 to the fourth is 256. We found it. Y equals 4 is the solution to this equation. Since y equals 4, and we know y equals x to the x, we can say that x to the power of x equals 4. This is another simple power equation. We need a number that, when raised to itself, equals 4. By inspection, x equals 2. Let's check it. 2 to the power of 2 equals 4. This is correct. So, our solution is x equals 2. This method was much more direct. It worked because the original equation was perfectly structured to reduce to simpler forms. It's important to understand why this worked. The original equation was a tower of exponents where the structure x point x point x allowed us to identify a repeating pattern, x point x. By recognizing this pattern and making the correct substitution, the problem simplifies dramatically. This is a crucial skill in algebra and problem solving. Now, let's rigorously prove that x equals sine 2 is the only real positive solution. We've found a solution, x equals sine 2, and we have a strong suspicion it's the only one. Let's prove it. To prove uniqueness, we can consider the function f of x equals x to the x. Our problem is to solve f(x). A simpler way is to analyze the function g of x equals x to the x. Let's look at the function g of x equals x to the x. Using calculus, we can find the minimum of this function. First, we rewrite it as g of x equals e to the power of x ln x. We take the derivative using the chain rule. The derivative is g prime of x equals x to the x times the quantity 1 plus ln x. To find the minimum, we set the derivative equal to 0. We need g prime of x to be 0. Since x to the x is always positive, we only need to solve 1 plus ln x equals 0. This gives us ln x equals minus 1, which means x equals e to the minus 1 or 1 over e. At this point, g1e is the minimum value. This is approximately 0.69. For x values between 0 and 1 over e, the function decreases. For x values between 1 over e and 1, the function decreases from 1 to 0.69. For x greater than 1, the function increases from 0.69 towards infinity. And at x equals sine 1, g1 is 1. Since x must be greater than 1 for our tower of exponents to make sense and grow, we only need to consider the increasing part of the graph for x is greater than 1. The function gx equals x to the x is strictly increasing for x greater than 1. This is a very important fact. It means the function never repeats a value for x is greater than 1. Now let's apply this to our equation. We had the equation x to the x equals 4. Since the function h of x equals x to the x is strictly increasing for x greater than 1, it can only equal 4 for one unique value of x. We already found that x equals sine 2 works, because 2 to the second is 4. Thus, x equals sine 2 must be the only positive solution. So, we've not only found the answer, x equals sine 2, but we've also used calculus to confirm it's the only one. A neat combination of algebra and analysis. Let's quickly recap what we've learned, and how to solve this and similar problems. Our problem was to find x in the equation x to the x equals 256. First, we saw that trying to find simple patterns with repeated exponents, like 4 to the 4th, can be misleading due to the tower structure. It's not always safe to just match bases and exponents. We then explored an algebraic method using logarithms and the Lambert W function, which is the most rigorous way to solve this type of equation in general. This gave us the exact solution, x equals e to the w of ln, 256. Finally, we found the simplest and most elegant solution. Recognize the repeating pattern. We rewrote the equation as x to the x raised to the power of x to the x equals 256. By making the substitution y equals x to the x, we simplified the problem to y to the y equals 256. This revealed y equals 4. And substituting back, we found x to the x equals 4, which means x equals 2. The key takeaway is that when you see towers of exponents, look for repeating blocks and make substitutions, and always remember to verify your answer. Thank you for watching. I hope this helped you understand how to approach these interesting exponent puzzles.